Friction on inclined plane. So have a look at this diagram where we have an object capped on a flat horizontal ground. Now there is no applied force here, which means the value of friction will be zero. Now what do we do? Instead of a flat ground, let's create an inclined plane. An inclined plane has an angle of theta, which is called the angle of inclination. So let theta be the angle of this incline. So now read, because of this incline, friction will start to act on the block. And why is that? Because once you have an angle of inclination, the block has a tendency to go down the plane. Even though the block has a tendency to go down, still it is possible that the block can be at rest. And how is it possible? Because friction is acting up the plane. Now, since the block is at rest, that is why the friction involved is static in nature. So, if we increase this angle of inclination theta, so let's read. As theta keeps increasing, this friction, the static friction, increases from 0 to a maximum value. So, static friction was 0 in the first situation, but as you keep increasing the value of theta, static friction value will keep on increasing until it reaches the maximum value, which we know is called the limiting value, limiting friction. Now consider another situation where we have increased the angle even further. Now assume even in this situation, the block is still at rest. Now since the block is at rest, even in this case, the friction involved will be static in nature. But the only difference is the value of static friction here in case number 3 will be greater than the static friction in case number 2. Because the point is, as the value of theta keeps increasing, friction also keeps increasing from 0 and it will keep increasing until it reaches a maximum value, which is called the limiting value. So at a particular value of theta, the block will just start to slide down the inclined plane. So imagine this case number 4, where theta is quite large enough where the block is just about to move down the inclined plane. And that is why the friction involved in this case is the maximum possible. Now, remember the maximum value of static friction is called limiting friction. So in this situation, when the block is just about to move, the friction involved is limiting. Now, what if you increase this angle even further, which comes the last situation? If the angle theta goes beyond this particular angle where the block was just about to move, if you increase the angle even further, then the block definitely starts to accelerate down the incline. So the block is going to move. Now, since the block is actually moving, now the friction involved will not be static anymore. It will be dynamic since the block is actually moving. And now let us try to figure out the values of the static frictions, limiting frictions, and dynamic friction. Here we can see a block which is kept on an inclined plane. Step number 1, like always, draw the forces acting on this block. So there are 3 basic forces acting on the block. One is the weight mg, then we have the normal reaction, which is the contact force, and then we have a friction, which is trying to stop the block from going down the plane. And that's why friction always acts up the inclined plane. Now, to solve questions, it is very important to resolve the mg into 2 components. One component will balance the normal reaction and the other component will balance the friction. So let's see how do we do that. So this is the same diagram. Mg component along the normal reaction side, this is mg cos theta, and the other component of mg will be mg sin theta. So as long as the block is at rest, mg sin theta and the friction will be equal to each other. But in every situation, no matter what is the angle theta, the normal reaction and mg cos theta, they are always equal. And why are they equal? Because observe, the block is not moving in this particular direction where my cursor is currently hovering. Since the block is not moving up and down, so the forces in this direction need to cancel out. So normal reaction and mg cos theta should be equal to each other. Like I earlier said, till the time the block is at rest, the downward force mg sin theta needs to be equal to the static friction. Mg sin theta is equal to F, where F is static. Static because the block is at rest. Now, like we discussed earlier, if you keep increasing the value of theta, so look here, we have mg sin theta. If theta keeps on increasing, the value of sin theta also will keep on increasing, which means F, the static friction value, will also keep increasing. So as theta keeps increasing, friction definitely increases. But friction cannot increase forever there is a limit to which the friction can increase, which we know is called the limiting friction, FL. And the value of FL, the formula is mu L times the normal reaction, where mu L is called the coefficient of limiting friction, and N in this case was mg cos theta. So the value of FL will be mu L mg cos theta. Now remember that situation when the friction reaches its maximum possible value, which is called the limiting friction, that theta is the case. At that angle, the block is just about to move. And if we increase the angle even further, then the block will start to slide down the inclined plane. So let's take the situation when the block is just about to move on the inclined plane. Step one, like always, draw the three forces acting on this block. Then we resolve the mg into two components. The n and mg cos theta will be equal to each other. And since the block is just about to move, so the downward force mg sine theta will balance the limiting friction. So mg sine theta is equal to F, and the friction involved is limiting in nature, which is the maximum static friction. So it is mu mg cos theta. Now since mg sine theta and the friction value are supposed to be equal to each other, so let's equate them. Mg sine theta will be equal to FL, which is mu s mg cos theta. So if we simplify this expression, mg will get cancelled out, and if you simplify, we will get tan theta is equal to mu s. Since sine theta upon cos theta is tan, this is the final expression. And hence we can say that the angle of incline at which the block is just about to slide on the inclined plane, that value of theta is given by tan inverse mu s. So in the exam questions, whenever the question asks you to find that critical angle when the block is just about to move on the inclined plane, we have to find the value of tan inverse of mu s, where mu s is the coefficient of static friction. Now let's summarize the entire situation. So we had all these cases, 5 cases overall. In the case 1, the block was kept on a flat ground, friction was 0. In case 2, we have an incline, and in case 2, case 3, case 4, we are actually increasing the value of theta. There will be a critical situation where the block is just about to move. In that case, the friction is maximum, which is called the limiting friction. Now, at this particular case, when the block is just about to move, we just discussed the value of the incline theta is tan inverse mu s. Now, analyze carefully from case number 1 till case number 4. The block is still at rest. And since the block is at rest, we can say acceleration of the block is 0. To summarize, we can say that the block is stationary if the angle of the incline is between 0 and tan inverse mu s. Till the time the angle is between these two values, the block will always be at rest, and hence acceleration is equal to 0. Now, the moment you go beyond this angle, theta, if theta is greater than tan inverse mu s, that's when the block will accelerate, and the friction acting on the block will be dynamic in nature. All kinetic friction will be applicable here. So to summarize, for the block to start moving, the angle of theta needs to be greater than tan inverse mu s. And to solve the questions, you are just supposed to remember these conditions. Greater than tan inverse mu s, the block will start to move. Less than or equal to, if theta is less than or equal to tan inverse mu s, then the block will be stationary and the acceleration of the block is 0. Now let's identify, once the block starts to move on the inclined plane, what is the value of acceleration? So as you can see in this image, the block is actually moving, which means the value of theta is greater than tan inverse mu s. Step 1 is to draw the three forces mg, normal reaction, and kinetic friction. Then we resolve the mg into two components, mg cos theta and mg sin theta. We discussed this already. For the block to start moving, the value of theta needs to be greater than tan inverse of mu s. Now we are supposed to find the value of acceleration. And how do we do that? Using the Newton's second law. Acceleration is equal to net force divided by mass. So as we discussed earlier, the normal reaction and mg cos theta will cancel each other out. So the net force will be along the incline. So we have mg sine theta going down the incline. Kinetic friction is acting up the incline. So what will be the net force? It will be the subtraction between these two forces. So the net force will be mg sine theta minus the kinetic friction. And the kinetic friction is mu times n. N in this case is mg cos theta, which means eventually the net force is mg sine theta minus mu k mg cos theta. So we put this value of net force in this expression to get acceleration. Net force divided by m. And if you simplify this expression, the m will get cancelled out. Finally, the expression for acceleration is g sine theta minus mu g cos theta. So this is the acceleration when the block is sliding down an inclined plane. To summarize, look at the two situations. If the inclined plane is rough, acceleration is g sine theta minus mu g cos theta. In case the inclined plane is smooth, so there will be no friction, which means the value of mu will be 0. In that case, this factor will be gone. So this will be 0. Eventually, we just get acceleration is equal to g sine theta. And these are the expressions which we can directly use while solving questions.